All right. So, welcome to chapter 10.2, where we talk about doing inference on the correlation coefficient using simulation-based approach. I'm going to start today's lesson off in a way that's going to seem perhaps a little bit odd, but bear with me. I want to show you something that I think is kind of a fun part of statistics and something that relates to my research, but it's going to start off a little weird. So, here we go. So, who remembers Sesame Street?
One of these things is not like the others. One of these things doesn't belong. Can you tell which thing is not like the other by the time I finish this song?
All right. I have a toddler, but that song relates very heavily to my research in that my research involves showing people pictures like this and asking them which one of these plots is not like the others. And hopefully, when you guys are looking at this particular set of plots, you all come to the conclusion that 12 is the one that's a little bit different. But stop for a minute and think about why. For me, at least, the reason why is that the shape of the cloud of points is different. There's a long, skinny, diagonal shape rather than a blob. And the reason that we pick up on that, statistically, we've done what's called visual inference. So we've looked at a set of plots and picked out the one that was different, and then we've tried to describe why. We're going to be doing exactly the same type of thing using simulation without the requiring a human to pick out the plot that is different. All right? So that's a tiny little portion of the research that I do, but it also happens to relate pretty heavily to what we're talking about today, which is how to do simulation for two quantitative variables when what we're interested in is how correlated are these two variables. Okay? So, given that we have data that looks something like this, where we have an x value on the left, a y value on the right, and they're connected, if we have a null hypothesis that says we don't have a relationship between x and y, how do we simulate that? Well, if there's no relationship between x and y, then it doesn't really matter which x value is connected to which y value. So let's just change which ones are paired together. Right? Turns out that doing that is the same as shuffling the order of the y values and keeping the order of the x values the same. And then we just fit a new regression or calculate the new correlation based on these new pairs of values. All right? And if we go back a few slides, that's exactly what we did to generate the 19 plots that are not the original data for this test, which incidentally is called a lineup. After the criminal procedure, we have one of the plots that's guilty and 19 that are not. So that's exactly what our simulation procedure ends up doing, is creating things that are not associated, right? And instead of using a plot, what we're going to use is a statistic, that is the correlation coefficient, to describe different. All right? So our null hypothesis is that there's no association between x and y. As a reminder, correlation coefficient is represented by the variable r when we're talking about the sample. So the population symbol for r is the letter rho, which is, it's a Greek letter that's equivalent to r. So our null hypothesis would be that rho equals 0. One repetition of our simulation is re-randomizing all of the response outcomes and matching that to the explanatory variable values. So that's randomize y, shuffle y, keep x the same. And our statistic is the correlation coefficient, r. Okay? All right, so again, here, plot 12 contains the original data. You can get a sense of what shuffling y looks like, because as soon as you shuffle y, the linear relationship between x and y goes away, right? And we end up with this cloud of points that just kind of looks random and somewhat boring. All right. So, our simulation-based inference for the correlation coefficient, we have a null hypothesis that is that there is no linear relationship between x and y. That is, rho is 0. We have an alternative hypothesis that there is a relationship between x and y, so rho is not equal to 0 usually. You could, in theory, have a alternative hypothesis that says that there is a positive relationship between x and y, so rho is greater than 0. But generally speaking, the problems that we'll do are mostly concerned with, is there a relationship, rather than which direction is the relationship. So the letter rho is the population version of r, and even though it's the Greek letter for r, it tends to look a little bit like p. So please be careful when you write rho. Make sure that you don't confuse it with p. It's not a proportion. It's not a p-value, right? It's a correlation coefficient. All right? So just be careful. All right. So back to our data set here. We've got the same head size and brain weight that we worked with in 10.1. And our sample correlation coefficient is 0.7996. So our null hypothesis in words is that there is no linear relationship between head size and brain weight. So rho equals 0. Our alternative hypothesis is that there is a linear relationship between head size and brain weight. That is, rho is not equal to 0. If we use our 3 S's strategy, our statistic is the correlation coefficient. Our simulation is that we assume that there's no relationship between head size and brain weight. We shuffle the values of y, so we shuffle the brain weights. And for each shuffled set of values, we calculate the correlation coefficient from the simulated data. And then we look at the distribution of all of those simulated correlation coefficients, and we compare that distribution to what we observed, our statistic, right, from our sample. And just as we used to draw the plots and have to draw the vertical lines and the arrows corresponding to the direction of the alternative hypothesis, we can do the same thing here, except there's nothing to shade in because our simulated correlations are all very neatly between negative 0.25 and 0.25, and our sample correlation coefficient was like almost 0.8. So we don't have anything to shade in at all. All right, so our p-value here for this simulation is less than 0.001, right? If we did 1,000 simulations, we can only say that it's less than 1 over 1,000. We can't say that it's exactly 0. Okay, so with that, our conclusion is I reject the null hypothesis that there is no linear relationship between head size and brain weight with p less than 0.001. There is a very strong there is very strong evidence that the linear relationship observed between the variables did not occur due to random chance, and thus we must conclude that there is a linear relationship between head size and brain weight. That is, rho is not equal to 0. All right? And that's really all that we have to do a simulation study for the correlation coefficient. It's pretty straightforward. I've intentionally not been using the examples in the book to give you the option of going through and looking at the examples and the explorations in the book and seeing how those problems are worked through with different data sets and different correlation coefficient values. So I'd recommend that you take a few minutes to look through another example there. But we are done with section 10.2. So thanks. I hope you are all staying safe and that you are all healthy and that you're not climbing the walls too much from this whole social distancing thing. So we'll do 10.3, 10.4, and 10.5, and then we will be done. So we've got 3 lecture recordings to go. Yay! All right. See you guys later.